Graph data is everywhere, from social networks and cybersecurity to biology and transport systems. But querying massive graph datasets distributed across multiple servers is still a big challenge. Our project, titled High Performance Graph Query Processor for Distributed Graph Database Server, aims to solve this challenge by implementing a scalable and efficient graph query engine on top of Jasmine Graph. We use the Cypher query language integrated with Hadoop Distributed File System, HDFS, for data ingestion, and developed a React-based front-end for query submission and real-time visualization. This system supports distributed execution, streaming results, inter-worker communication, and even query status notifications, making it well-suited for large-scale real-time applications. Let's move on to the demonstration. The Jasmine Graph master node is deployed on the university's Gen 9.1 server, while the worker nodes run on the Gen 9.2 server. After starting the Graph database server, we can observe logs showing the master node connecting to each worker using their IP addresses and port numbers. In this demo, we're using a 4-worker setup. First, we run the query match n return n to retrieve all vertices. Since the dataset is too large to load entirely into memory, our system returns the data as a stream. A single vertex may appear in multiple partitions due to central edges. To eliminate redundancy, we assign each vertex a unique partition using a metadata property called partition ID. The number of results matches the expected values for the opinion dataset. Similarly, for edges, we run match n r m return n m. Central edges also exist in multiple partitions, creating duplicates. To manage this, we use an edge meta property to assign each central edge to a specific partition. This approach lets us treat all partitions as a single logical graph. Again, the edge count aligns with the opinion dataset. Next, let's consider a traversal query, finding 2 length connections of a specific vertex ID. We use match n r m d s, where ID n equals 13, return n m s. Here, once the system finds m, it may need to access s via another partition. To do this, the worker handling n sends a subquery to the worker where m resides. This interworker communication is visible in the logs and enables complete traversal results. Finally, for aggregation, like getting the average of IDs, we use match n return average n ID. Each worker performs local aggregation, and the results are combined by the master for global aggregation. This model efficiently handles distributed query challenges. This is the front-end application of our system. After logging in, users are redirected to the cluster management page, where they can manage multiple Jasmine Graph clusters. To run queries or visualize data, the user must first select a cluster. Once selected, the user is taken to the Graph panel. In the Graph panel, users can upload graph datasets and visualize them directly in the browser. The graph visualization is designed in a 2-level structure. At the first level, users see a partition view, which represents how the graph is distributed across workers. Clicking on a partition node drills down into the node-level view inside that partition. The front end supports 3 types of graph visualizations: full view, in-degree, and out-degree views. To begin, users select the visualization type from the drop-down menu, and then choose the desired graph. Once loaded, the partition-level view is displayed, where users can explore each partition and examine the corresponding partition details, such as node count and edge distribution. In the queried interface, we can run Cypher queries directly from the front end and view the results in row format, table view, or even as a graph visualization. And that wraps up our demo. Thanks for watching. Hope you enjoyed seeing how our system handles large-scale graph queries in a distributed setup.